all of you. Myself, Kanika Sharma. I am working as assistant professor in the Department of Electronics and Communication Engineering since 2004. So today I will let you know about what are embedded systems, how they are classified according to their demands and according to their applications into three broad categories, and what are the different applications of embedded systems, and how these embedded processors are useful in our today's life. So, as we all know that our day-to-day life is becoming more and more dependent upon these embedded systems and technologies and digital techniques. So we should that your embedded technologies are blending into our daily activities even without our knowledge. The fact is that your embedded systems, which contain your in refrigerators, washing machine, DVD players, and in washing machine, DVD players, and in many other electronic gadgets, they used in different types of equipments. So you may be traveling through Honda or Toyota or Ford vehicles. So genius players are working behind the different features which will provide these luxurious vehicles to us. And these features are varying from, you can say that ignition control system to the intelligent headlamp controllers and to the complex airbag control systems which will protect us from some severe accident. So we can say in general that embedded systems are just like reliable servants which do not like to reveal their identity. Neither they complain about the heavy workload assigned to them by the users or by their bosses. They're just sitting at some hidden place and try to execute their dedicated task till their last breath. So today's session will include these embedded systems only, their applications and classifications. So we can say that in general the definition of embedded system is an electromechanical system which is basically designed to perform a specific function, and it is a combination of both hardware and software. In some scenarios, an operating system can also be introduced. It can also be a part of that embedded system. So we can say in general that your embedded system contains two main components, that is hardware and software, and some other scenarios it may contain your real-time operating systems. So the different applications or examples of embedded systems are microwave ovens, refrigerator, DVD players, music systems, modern vehicles like your BMW 7, Mercedes S, right? Mobile phones, digital camera, and computer systems, and many more. So the main components of embedded systems are hardware, its application software, that is its firmware, and real-time operating systems. Now what is RTOS? As I have told you that it contains your hardware and its application software, its application-oriented software or its firmware. So in hardware, it may contain your microprocessor, microcontroller, ARM processor, MIPS processor, that is microprocessor without interlocked pipeline structured processor, or it may contain Intel NMX processor depending upon the application, and its related firmware will also contain in that embedded unit itself. So in some scenario, it may contain your operating system, that is a real-time operating system. Now, what is real-time operating system? How it is different from general-purpose operating system? General-purpose operating systems are just this Windows and Linux. These are your general-purpose operating systems. And real-time operating systems, like Linux is your real-time operating systems. General-purpose operating systems. In general-purpose operating system, we have your Windows, Windows XP, Windows 7, and many more. Now these real-time operating systems, which may be part of your embedded system, the objective of this real-time operating system is to provide their services to the users within strict time deadlines. Like example we can take, that is the launching of a satellite. The launching of a satellite should be, the vehicle should be launched within the specified strict time deadlines. So we can say that these operate in constrained environments in which computer memory and processing power are limited. So now what is the main part of this RTOS which will carry out or which will provide these basic services to the users? That is the kernel. So kernel is the part of the operating system which provides the basic services to the users. Now what are those basic services? The first one is the inter-task communication. intertask communication. Then we can have dynamic memory allocation, then device IO input output supervisor, and we can have intertask communication and synchronization, and the management of all these tasks, which will be a part of your basic services. So we can say that in general that your kernel provides the abstraction layer between the hardware and the software. This is just a diagram which shows that RTOS provides the abstraction layer between the hardware and the software. So the next is the classification of embedded systems. Now, how do we classify these embedded systems? How these embedded systems, which is a very broad category, how these embedded systems are classified into different groups. So these are classified into three main groups, that is small scale embedded systems, medium scale embedded systems, and the third one is the sophisticated embedded systems, or in some books they may write large scale embedded systems. Sophisticated, large scale are the same things. So the first one is the small scale embedded systems. This small scale embedded system comprised of single 8-bit or 16-bit microcontroller. In single 8-bit microcontroller we can have 8051 microcontroller, and 16-bit microcontroller we can have PIC microcontroller. So it may consist of some little hardware and software complexities. In that case, your C or Java will be used as a development platform in order to generate the firmware, which is a part of your this embedded system, that is the application software of that particular hardware which we have used for the small scale embedded systems application. Now the different applications are the fan regulation, then software, or digital calendar, and if we want to show some messages, in that applications we use small scale embedded systems. The second category is the medium scale embedded system. Now in this category it contains of single 16-bit or 32-bit or few number of 16 32-bit microcontrollers. Now in case of 32-bit microcontrollers we have ARM type of processors, ARM type of embedded processors. ARM stands for, that is, Advanced RISC Machine. Now these type of embedded processors use complex software design tools like CFID, RTS, some real-time applications. They may be employed in some real-time applications. So the different applications in which we can use this medium-scale embedded systems are, the first one is the microcontroller, your small robotics application, then coffee vending machine, and in-home automation also. So these are the applications of medium-scale embedded systems. The third category is the sophisticated or large-scale embedded systems. Now in this category we can have enormous hardware, we can have a very you can say complicated type of hardware, and it requires some software complexity. So in that case we can use PLD device, that is FPGA type of device, for its generation of the software part, and also for the implementation. And the applications include your robotics, the metros, and the mobile phones which we are using nowadays, right? So the big applications in which this embedded system, sophisticated embedded system, have been used was the NASA X-38 project. In this project they have developed a rescue boat which will be used by the International Space Station in order to save the life of the astronauts, right? So these are the different applications of sophisticated type of embedded systems. So we have learned that your embedded system contains of three main components. Basically, it contains of two main components, that is hardware and its application software. It may also known as embedded firmware. And in some applications it may contain your real-time of operating system. So in that case we can say that your embedded system consists of three main components, that is hardware, its application software, that is embedded firmware, and the third one is the real-time operating systems. In real-time operating system, what we have learned that there is a kernel which provides the basic services to the users, and this also provides the services within the strict time deadlines, right? And what are those services? Like your inter-task communication between the different tasks, then task management, device input-output supervisor, and we can also have timers in that case. After that, we have learned the classification of embedded systems. The embedded systems are classified into three categories, that is small scale, medium scale, and large scale or sophisticated type of embedded systems. And we have seen that there are different applications in which we can use a small scale, medium scale and sophisticated type of embedded systems. Now the next one is again the application of embedded systems in home automation. Now as soon as a person opens the door of a home, its surroundings may provide comfortable environment to him or her. So as soon as he opened the door, his four LED television may start, then fan may get started, then this power sensor may get up, may starts up, then power sensor, reminder sensor, all will be get into the picture. The next application of these embedded systems in the automobile industry. Now, as I have told you that your this embedded systems in ordinary cars, your embedded systems may vary from 20 to 40 in number. Whereas in case of luxurious cars, like BMW 7 or Mercedes S, they may contain 75 to 100 number of embedded systems. As an example, we can say that the first embedded system used in the automotive application was the microprocessor based fuel injection system, which was introduced by Volkswagen 1600 in 1968. You can see that so many years back this embedded system had been emerged, right? So we can say that in automobile industry, this embedded system provide the features from the intelligent headlamp controllers to the engine control system, to the ignition control systems, to the complex airbag control systems, which will protect us from if some accident by chance occurs in that case, right? So this is an example, a picture I have taken, that in 2002 Opel Vectra has emerged, which will have over 40 sensors of different 25 types of sensors was introduced. Now the next concept in embedded systems is system on chip. Now what is system on chip? As according to Moore's law, the number of transistors gets double after every 2 years, approximate after every 2 years. So today's chip may contain more than 500 million transistors. So as in PLD devices, what we have, PLD device is the programmable logic device. That is a device which can program according to the given logic. They are classified further into 3 categories, that is SPLD, that is simple programmable logic device, CPLD, that is complex programmable device, and the third one is the FPGA type of device. So the number of transistors in case of FPGA is very high as compared to your CPLD. That is the limit, where the limit of CPLD ends, there the limit, this is the starting point for that of your FPGA type of device. So we can say in case of your SoC, what we have your number of blocks, and these blocks are interconnected with different type of buses. That is the type of buses which through which these blocks are interconnected are AMBA buses. That is Advanced Microcontroller Bus Architecture, which is provided by the ARM Corporation. Now in case of this SoC, that is system on chip, your number of blocks are interconnected with each other. Now from the PCB, the evolution of SoC from the PCB to SoC contains these type of different processor. It may contain one or more microcontroller, microprocessor or DSP cores, memory blocks including a selection of ROM, RAM, ESCAPE, PROM and flash, timing sources which includes your oscillator, which are actually required for the execution of the instruction. This will provide the timing and the control signals which are required for the execution of the instructions. Then the peripherals including counters, timers and power on reset generators. The next one is the external interfaces, which includes your industry standards such as USB, Ethernet and USART. Analog interfaces include your ADC, DACs, and voltage regulation and power management, which may also part of your SoC. So we can say that SoC contains any type of processor depending upon the application. It may also contain these type of other units on a single chip. That is, your whole system is spread on a single chip. So in our mobile phones, what we have SoC only, right? So these are some other example of SoC, that is camera on chip, and the second one is the solar power wireless sensor, which is provided from the Berkeley Corporation. These are very small size. Now, if it is not possible to construct a SoC for a given system, what will we do in that case? We go for some other alternate, we go for some other option. In that case, we have system in package or multiple chip module. So in case of SIP, in case of multiple chip module, if it is not feasible to construct a SoC for a given system, we will opt for this option. And in this case, we have number of chips. For all those blocks which are available in SoC, for each block we have a chip in this SIP, that is in case of multiple chip module. And these chips are stand either in a horizontal or in a vertical fashion. And also these are connected by either a proprietary or industry standard bus such as the AMBA bus, which is available from the ARM Corporation. Now AMBA stands for Advanced Microcontroller Bus Architecture. This type of buses is widely used as the on-chip bus for the ARM processors. And AMBA buses which were introduced was the advanced system bus, advanced peripheral bus. Nowadays we have advanced high-speed bus also, with again from the ARM Corporation, that is from the AMBA buses, which is available from the ARM Corporation or ARM type of processors. Now the next category is the embedded processor. Till now we have discussed our knowledge for embedded systems, then classification of embedded systems, its components, its different application of embedded system in automobile industry, and then the concept of SoC. Now the next one is the embedded processors. Now what is an embedded processor? An embedded processor is a special microprocessor or microcontroller that performs fast, precise, and intensive calculation for complex real-time applications. Why it is so special? Why we call that it is a special microprocessor or a microcontroller? Because this type of embedded processor provide the applications in some specified manner. Right? Now, as your general processor, microprocessor, that is 8085 type of processor, provides application in some general behavior, in some general manner. Whereas if some special type of processor is used for embedded computation, in that case, it requires that it provide their application in that particular specified, with that particular specific objective, right? So this type of processor performs fast, precise, and intensive calculations for complex real-time applications. Now, how we can say that it is a fast type of embedded processor? There should be some pipelining architecture, right? There should be some power saving feature should be provided within that type of embedded processor, and they must provide intensive calculations for some complex real-time applications. Examples include your ARM processor, Intel multimedia processor, MIPS processor. Now, what is ARM stands for Advanced RISC Machine. We will go into the nitty-gritty of these technologies also. ARM is your Advanced RISC Machine, Intel MMX is multimedia processor, and MIPS is microprocessor without interlocked pipeline structure. Here M stands for microprocessor, I stands for interlocked, without interlocked, P stands for pipelining structure. Some students may confuse with the MIPS processor or with the MIPS speed. In that case, your MIPS provides a million instruction per second. That is execution of instructions, million instructions per second. That actually denotes your speed of that processor. But here, embedded processor, that is MIPS, stands for microprocessor without interlocked pipeline structure. Now, the first one is the ARM processor. Now, this ARM processor, that is Advanced RISC Machine, is a 32-bit RISC processor architecture. This is a 32-bit wide, developed by ARM Limited, that is widely used in number of embedded designs. We can say that around 75% of applications available in the market for embedded industry, they are built around these ARM type of embedded processor. Now, what makes it so important, so powerful? The first one is its power saving feature. Because of its power saving feature, ARM CPUs are dominant in the mobile electronics market, right? Where low power consumption is the critical design goal. Everyone wants embedded system, but its power consumption should be low, right? We can say that MIPS per watt should be low. That is, the execution of million instructions per second per watt. The consumption for the execution of that much instructions per watt should be low. So we can say that we want that there's some embedded system which have low power consumption ratio. Now, why do we require ARM here, that is in embedded systems? ARM is one of the most licensed and thus widespread processor cores in the world. It is used especially in portable devices because of low power consumption and reasonable performance, that is MIPS per watt, which I have already told you. The third important feature is the several interesting extensions available, which includes your thumb instruction set. Besides its own instruction set, there is an instruction set which is known as thumb instruction set. Now, the various processor codes for ARM processor are ARM6, ARM7, 9, 10, 11 and many more. ARM6 was the first developed ARM processor which is available without the thumb instruction set. From ARM7, the company have incorporated the thumb instruction set. Beyond these, all type of processor, ARM type of processors contain a thumb instruction set. So, your ARM7, you can say that what ARM7 contains. It is actually known as TDMI architecture. T here stands for thumb instruction set. D stands for debug interface. M stands for multiplier. And I here stands for fast interrupts. Right? Now, debug interface. Debug interface is actually your JTAG, which is available from the IEEE standard 1149.1. JTAG is Joint Text Action Group. This basically provides the ISP feature, that is in-system programmable feature. The ISP feature is the ability to reconfigure the logic and the functionality of the device. So JTAG basically provides that ISP feature, which further yields with the faster time to market. Now, what this ARM type of architecture contains? The ARM architecture includes the following RISC features. The first one is the load and the store architecture. That is, firstly, it will load the data. What we have actually for the execution of instruction, what are the three main processes? The first one is firstly we will fetch the instruction, then we will decode that instruction, and finally we will execute that instruction. So we can say this is basically your three-stage pipeline architecture. Simple ARM7 type of ARM processor. So firstly we will load the instructions, then after the execution of the instruction we will store the data also, we will store the result also. The second feature is the orthogonal instruction set. That is, we can use any instruction. All the instruction will have the same format. We can use any type of register, any type of addressing mode. Right? So all these instructions are orthogonal in nature. Whereas in case of your 8085 type of processor, 8051 type of processor, microcontroller, sorry, uh, in that case we have non-orthogonal instruction set, right? For each instruction, the addressing mode will be fixed. There are a number of addressing modes: direct addressing mode, indirect addressing mode, immediate addressing mode, right? So for each addressing mode, the register is specified. But in this case, ARM processor, the instruction set is orthogonal. That is, interchangeably we can use any register, any addressing mode. The register file is very large, which provides 16 general registers, general purpose register, and each register is 32-bit wide. Then fixed instruction width of 32 bits to each decoding and pipelining. That is, each instruction will be of 32-bit. So besides its own instruction set, which will be 32-bit wide, it provides a thumb instruction set, right? Now ARM architecture is of pipelined architecture. In ARM 7, it provides 3 stages, that is, firstly fetching, decoding, and execution. Whereas if we compare this ARM 7 with the ARM 9 version, in ARM 9 what we have 5-stage pipelined architecture. Firstly it will load, then it will fetch, firstly it will load, then fetch, then decoding, then execution, and the last one is the storing. One human bus architecture. In case of your ARM 7, it used your one human type of architecture, and in ARM 9 it used your hardware type of architecture. That is, different caches, different buses are used in order to access the program memory and data memory in case of hardware, whereas in case of one human, same buses are used in order to access the program as well as the data memory. 18, 16, 32-bit types, data types are available. Simple structure, reasonable, good speed per power consumption ratio. So in the embedded industry, everyone wants that the power consumption should be very low. Even though we used our mobile phones, but we actually prefer those mobile phones which consume power in a very low manner, right? So thumb, new ARM processor have a complex instruction set called thumb that uses a 16-bit wide instruction encoding. So besides its own instruction set, which is 32-bit wide, ARM 7 uses a thumb instruction set which provides their instruction set which is 16-bit wide. And why, in which situations we can use particularly these type of thumb instruction set, where the memory port or the bus width is constrained to less than 32 bits. Then we will go for these type of thumb instruction set. The first processor with a thumb instruction decoder was the ARM 7 TDMI, which I have explained you. After this, all the versions of ARM processor, that is ARM 7, 9, 11, all these processors contains your TDMI type of architecture, except your ARM 6, which was without TDMI structure. This I have already explained you. Now ARM 7 register set. ARM 7 register set contains, as I told you, that it contains large register file. That is, it contains 16 registers, and each register is 32-bit wide. So we have R0 to R50 number of registers. 16 pieces of 32-bit integer registers R0 to R15 are available in ARM mode. R0 to R12 are general purpose registers. R13 is your stack pointer. So what is stack pointer? Stack pointer basically stores the address of the stack top. R14 is a subroutine link register which actually provides the address of the subroutine which is stored in some register. The address of that subroutine is stored in some register. It will indicate that. R15 is the program counter. This basically stores the address of the next instruction which is to be executed. And R16 is the state register, that is CPSR, current program status register, which will hold the address of the current program, current instruction. Okay. Now the next feature which attracts the mobile, which attracts this industry of embedded system for ARM is the condition code. Condition code, this is a very interesting addition to the ARM design, that is 4-bit condition code. That is, the execution of every instruction is optionally conditional. What does it mean? Suppose we let us take an example. that is loop compare Ri Rj, that is compare the contents of Rj resistor with Ri. So here we set condition not equal, greater than or less than. So we can say if it is greater than, then this should be happen. If it is less than, then this should be execution. Or if it is not equal, then it should loop to some other other location, right? Another important feature, we have number of important features for this ARM type of processor. Another important feature which makes it that all embedded gadgets which are available in the market, approximately 75% to 80%, they are built around this ARM type of processor only because of these special features. Another important feature is the fold shifts and rotates into the data processing. Your high level language statement was in the C statement. We have this this is a simple C statement which is a high level language. Here what it actually reads with, that is shift the contents of the J resistor by 2 and add those shifted contents with the A resistor, with the contents of the A resistor, and those added contents will be stored in the A register. So how this statement could be rendered as a single word in a single second instruction on the ARM? Simply with this instruction, that is, let's shift the contents of the register J by 2, add the contents with the A registers, and the result will be stored into the A register. So this is the very important feature which will be provided by the ARM processor, that is to fold, shifts and rotates into the data processing itself. So as I told you that 75% of all embedded applications, they are built around this ARM type of processor. They are basically used in portable devices like your PDAs, mobile phones, media players, handheld gaming units and calculators. Right? So this is all about the ARM processor. So in ARM processor, what we have learned? We have learned that ARM stands for Advanced RISC Machine. In ARM type of processor, there are various versions which vary from ARM 6, ARM 7, ARM 9, ARM 11 and many more. ARM 6 was without TDMI structure. From ARM 7 we have TDMI structure, we have TDMI type of structure, and beyond all those it will contain of TDMI type of structures. And what TDO stands for, that is T stands for thumb instruction set, D stands for debug interface, M stands for hardware multiplier, and I stands for fast interrupts. D basically besides its own instruction set, it provides another instruction set which is known as thumb instruction set, which is 16-bit wide, right? And here the second one is the debug interface, which will provided with the help of JTAG controller, that is Joint Test Action Group, are available with the IEEE standard 1149.1, and this basically provides the ISP feature, that is in-system programmable feature. ISP, what is the precise definition of ISP? That is the ability to reconfigure the logic and the functionality of the device. Both these things, that is the logic and the functionality of the device, can be reconfigured with the help of ISP feature, which is provided by the JTAG. Right? After that, we have seen that your ARM 7 is your 3-stage pipeline structure, right? And ARM 9 is your 5-stage pipeline structure. ARM 3 basically follows your one human type of architecture, and ARM 9 follows your this hardware type of architecture, right? So and these are used in portable devices like PDAs, mobile phones, media players, handheld gaming units and calculators. And besides these, there are various important features which will make it so important that around 75% of applications which are built around this type of ARM type of processor. So what are those important features? That is power saving feature, then your multiple shift and rotate data processing in the data processing itself, and another important feature is the condition code, right? So these important features will make it to attract into the embedded market. Now the next embedded processor is the MIPS processor, that is microprocessor without interlocked pipeline structure. So students, do not get confused with the MIPS processor and the MIPS speed. In that case, your MIPS speed stands for the execution of million instructions per second. And for embedded industry, this MIPS per watt should be low, right? That is, the execution of million instruction per second per watt should be low. And here this MIPS stands for, which is a category of embedded processors, stands for microprocessor without interlocked pipeline structure. Now, this is basically a RISC type of microprocessor developed by MIPS technologies. The early MIPS architectures which were developed were 32-bit implementations, while later versions were 64-bit. So similarly, as we have ARM processor, ARM6, ARM7, 9, 11 and so on, we have different versions or revisions of MIPS processor also, which ranging from MIPS 1, 2, 3, 4, 5, MIPS 32 and 64 and further many more. Right. So, firstly, there is a term that is pipelining. Now, what do you mean by pipelining? Pipelining is the execution of the instruction, current instruction, while, that is the fetching of the next instruction while your current instruction executes. That is the instruction which is in hand that should be executed while your next instruction is to be fetched, right? So this is your pipelining. Now there should be some hurdle in the pipelining which make it MIPS type of processor. So what is that hurdle in the pipelining? That is, the interlocks has been set up to ensure that instruction that took multiple clock cycles to complete would stop the pipeline from loading more data, basically to pause while it completed, right? So these interlocks can take a long time to be set up. So other solutions which they have incorporated, that is that all instructions take only one cycle to complete. In order to reset these interlocks, firstly, all instructions should take one clock cycle in order to complete, thereby removing any need for interlocking. So this has been eliminated the useful instructions like mul and div, multiply and divide instructions. They are basically, their mnemonics are mul and div, so which would take multiple steps. The third is that now the chips could run at much higher clock rates. Okay, with these solutions, they run at higher clock rates. Also, your MIPS type of processor, they are 5-stage pipelined architecture. They follow 5-stage pipelined architecture. What are those 5 stages pipelined architecture? Look into the picture. The first one is the instruction. First one is the loading, then instruction fetching, then decoding, execution, and write back. That is storing. That is load and store architecture. So the first is the instruction fetch unit. This typically referred to as a load unit. Firstly, we will load the data. We will load the instructions in this case. Then the second is the instruction decode unit. This unit gets instruction from IF, that is instruction fetch, and extracts opcode and operand from that instruction. It also retrieves register values if requested by the operation. If it is requested in the operation in the instruction itself, then it must also retrieve the register value in that case, right? The third one is the execution unit. It runs the instructions typically referred to as the ALU in modern terminology, that is arithmetic logic unit. Then now these last 2 stages, that is memory access unit and write back unit, makes it different from the this ARM type of processor, that is ARM7. That is, the memory unit fetches data from main memory under the control of the instructions from the instruction decode unit and the execution unit. The last one, the last stage is the write back unit. This is typically referred to as the store unit in modern terminology. So we can say that your MIPS also for your store and load type of architecture, which was also followed by your ARM9 type of embedded processor. Right? So these are the embedded market of MIPS. These are some applications of embedded systems, in particularly in the using MIPS type of processors. Computer networking, telecommunications, video arcade games, computer printers, digital set-top boxes, digital televisions, cable modems, personal digital assistants. Now, one thing I would like to share with you is that from the first mass-produced embedded systems, that is Automatics D17, which was a very big computer, basically used for the guidance for the missile, right? To the recently launched Apple iPhone, which we are using nowadays, embedded industry has evolved a lot. Now, how this evolution has emerged? Now, this has been emerged in terms of miniaturization, performance, development cost, then we can say features, and the last, time to market, faster time to market, right? Time to market. So we can say that from the mass production of this Automatic 17 to the Apple iPhone, your mobile industry has emerged a lot in terms of these parameters, or in terms of these different aspects. So this is all about the embedded systems. So today we have learned about embedded systems, introduction to the embedded systems, the classification of embedded systems, right? Then we have components of embedded systems, then classification of embedded system, which comprised of three main categories, that is small scale, medium scale, large scale or sophisticated type of embedded systems. And then we have discussed SOC concept. Then we have come to embedded processors, and embedded processors which we have discussed are the ARM processors and the MIPS processor. Right? So this is all about the introduction to the embedded system. So there are so much to learn into this embedded system. This is the just introduction to this embedded system. So thank you so much for such a good being good in terms of good, right? So you can note down my email ID. This is Kanika Sharma80@yahoo.com. If you have among you, if you have any query about this introduction to embedded system or applications of embedded system, you